Formula One cars corner in a way that almost looks impossible. They generate more than 5 times the force of gravity in high-speed turns, requiring far more grip than tires alone could ever provide. Most people assume that grip comes from wings, but in modern Formula One, wings are only a small part of the story. The real reason these cars stick to the track is hidden underneath them, invisible, extremely powerful, and surprisingly fragile. It's called ground effect. And while the term gets thrown around constantly, very few explanations actually show how it works, why it's so efficient, and why it can suddenly stop working altogether. So in this video, we're going to break it down properly. What ground effect really is, how modern Formula One floors generate downforce through ground effect, why it's superior and more efficient than wings, and why it can also be one of the biggest problems in modern Formula One. Let's dive into it. At its core, ground effect is a way of generating downforce by controlling airflow beneath the car. If you can make the pressure underneath the car lower than the pressure above it, the car will be pushed downward into the track. That's downforce. But unlike wings, which operate in open air, ground effect uses the track surface itself as part of the aerodynamic system. The ground constrains the airflow, forcing it through carefully shaped passages under the car. This confinement massively increases the aerodynamic forces that can be generated without requiring huge wings or excessive drag. The idea dates back to the late 1970s, when teams realized the underside of the car was far more powerful than the top, if utilized correctly. Those early ground effect cars were incredibly fast, but also extremely dangerous. Modern Formula One represents a far more controlled, regulated version of the same principle. To understand ground effect, you need to understand the Venturi effect. The Venturi effect describes what happens when air is forced through a narrowing passage. As the cross-sectional area decreases, the airflow must speed up to conserve mass. This is known as the law of mass conservation and is described in the continuity equation. When air speeds up, static pressure drops. This relationship between velocity and pressure is described explicitly by Bernoulli's principle, but what matters here is the outcome. Faster flow equals lower pressure. Formula One engineers exploit this by shaping the underside of the car into aerodynamic tunnels that deliberately accelerate airflow. Instead of pushing air downward like a wing, the car pulls itself downward by creating a low-pressure, vacuum-like region underneath. Under a modern-era Formula One car are 2 large Venturi tunnels, one on each side of the chassis. Air enters these tunnels at the front of the floor through specially shaped air intakes. This incoming airflow is already highly disturbed by the rotation of front wheels, which is why teams use curved strakes, fences, and carefully shaped inlets to clean and guide the flow. As the air travels rearward, the tunnel gradually narrows. Eventually, it reaches its smallest cross-section, the throat. At the throat, the flow area is at its smallest, which has 2 direct consequences. Air velocity peaks and static pressure drops dramatically. This low-pressure region produces the majority of the car's downforce. But the tunnel doesn't stop there. After the throat, the tunnel expands toward the rear of the car into the diffuser. This expansion is critical. A larger exit area allows more air to leave the tunnel. That increased mass flow effectively pulls more air through the entire system, as the mass flow rate must remain constant to abide by the laws of physics, which it does. The diffuser doesn't create downforce by itself. It simply enables the rest of the floor to work harder. Think of it like suction through a pipe. The easier the air can escape, the faster it must flow upstream. What makes ground effect so powerful is how much of the car it acts on. Wings generate force over a relatively small surface area, which inhibits how much downforce they can actually create. A crucial point in aerodynamic force generation comes from the total area which you can utilize to generate a force. Ground effect acts across almost the entire floor of the car. That means more total force, better load distribution, and a lower center of pressure. This improves not just grip, but stability. Ground effect is also extremely efficient. Wings generate downforce by deflecting air, which inevitably produces strong vortices, induced drag, and energy losses. Ground effect relies primarily on pressure reduction, not aggressive flow deflection. Because the airflow is constrained by the ground, vortices are much weaker and induced drag is almost non-existent. Furthermore, the frontal area of the floor, which is being used to harness the ground effect, is almost negligible when compared to front and rear wings. This means its inherent pressure drag is almost zero, contributing to its amazing efficiency in terms of downforce to drag ratio. However, ground effect has a major weakness that traditional wings do not. It is extremely sensitive to ride height. As the car gets closer to the track, several things happen simultaneously. The gap between the floor and the ground shrinks. The airflow beneath the car is forced through a smaller passage. Its velocity increases, pressure drops further, and downforce increases. This creates a powerful positive feedback loop. More speed produces more downforce, which pulls the car even closer to the ground, further shrinking the tunnel and accelerating the airflow even more. But this process has a hard physical limit. If the gap becomes too small, the volume of air simply cannot fit through the tunnel at the required rate. At that point, the flow reaches a mass flow limit. This phenomenon is known as choking. Once choking occurs, the behavior of the airflow changes instantly. The Venturi tunnel can no longer sustain the low pressure region beneath the car. Pressure under the floor rises sharply, destroying the suction that was producing downforce. This loss does not happen gradually. It happens across large sections of the floor at the same time. Unlike a conventional wing, where performance degrades smoothly as conditions worsen, ground effect fails abruptly. And because this downforce loss occurs while the car is traveling at high speed, the suspension unloads almost instantly. The car rises. As ride height increases, the tunnel unchokes, airflow recovers, pressure drops again, and downforce rapidly returns. The car is pulled back toward the ground. This cycle of compression, choking, downforce collapse, and recovery can repeat many times per second. And that violent oscillation is what we all know as porpoising, a common theme for the 2022 Formula One cars. Ground effect also explains why following another car is so difficult, and why overtaking has been less exciting as of recent years. The airflow behind a car is very turbulent and low energy. Ground effect relies solely on clean, energetic, and undisturbed airflow to operate efficiently. This makes it very difficult for modern Formula One cars to follow each other in high-speed sections, as the majority of their downforce is generated by the floor. Without proper downforce generation via ground effect, the car's grip is greatly reduced, and overtaking suddenly becomes impossible. So why did F1 return to ground effect at all? Because when it works, nothing else compares. Ground effect allows huge cornering speeds, exceptional aerodynamic efficiency, lower reliance on extreme wings, and more downforce with less drag. The modern regulations of 2022 to 2025 aim to capture these benefits while preventing the extreme and dangerous behaviors of the past. And ultimately, they succeeded. However, its extreme sensitivity has made close racing and overtaking more challenging than originally intended. Despite its unmatched aerodynamic efficiency, ground effect is set to be scaled back again in the upcoming 2026 regulations. Ground effect isn't just another aerodynamic concept. It represents the peak of modern Formula One performance. Reintroducing it allowed engineers to achieve levels of downforce that traditional wings could never match. Mastering ground effect isn't about brute force. It's about control, balance, and operating on the very edge of physics. And it's that delicate balance that makes Formula One engineering so captivating. If you enjoyed this breakdown, consider liking the video and subscribing for more.